All right, I'm going to assume everybody can hear me. I'm Brian Ray. I'm the CTO of Link Labs, and thank you for joining today's webinar on the costs of LPWAN technology. Just so I don't have to stare at myself, I'm going to jump over to the screen share. All right. Today on this webinar, we're going to cover basically the elements of costs, things that go into the cost of building an Internet of Things connected solution of various types, generally that use LPWA or low power wide area network technologies. Then we're going to dig a little bit into networks and wireless technology options that are out there. And then we're going to finish up with some use cases where we actually go through the costs associated with addressing different use cases with various technologies. Before we begin, I just wanted to make this abundantly clear before we upset a lot of people. This webinar is not about firm claims about what things actual cost. This is really about how you think about costs and how you might use the thinking that we show here to build your own models for your own company, your own products. Certainly, if you're going to launch a product, for hundreds of thousands of dollars, you're going to go out and research for yourself what you can get connectivity from Verizon or Sigfox or whoever for. Don't take my word for it. The costs I'm showing here are just what I can find on open source. Certainly nothing proprietary or secret about what we're sharing here. So your mileage may vary. So I just wanted to point that out before we start. We've got a live chat going over here on the right. This is the first time we're doing the live chat. So I've got my friend Glenn over here who's monitoring that, and he's going to flag different questions that come up for me to answer live on the webinar. And if we don't get to your topic or you'd like to have a deeper discussion, jump on over to our forum site, which is forum.link-labs.com, where you can ask a question. Always post a new topic for a new question, and I get those immediately. I always respond. We've got a couple hundred people that use it pretty regularly, so hopefully you can spark a debate or discussion there. Okay, so Link Labs, just a quick intro to our company. We are an Internet of Things technology company based here in Maryland in the US. Our primary mission is to build and integrate complex industrial and enterprise IoT systems for our customers. We're very focused on location, using various technologies, GPS, Wi-Fi, Bluetooth proximity, and other things. You can check out our product called AirFinder, where we use Bluetooth low energy, and our product Symphony Link and LTE to combine to give very inexpensive and accurate asset tracking. From a technology standpoint, we're very focused on LTE Cat M1, Symphony Link, which is our version of LoRa, where we've taken the LoRa physical layer and added a bunch of features for industrial use, and then Bluetooth low energy, which many people are familiar with. If you're interested in how we can help, we do a lot of services work, actually building from from conception all the way through production and deployment of solutions. I set up this email address webinar at link-labs.com specifically for this webinar. Those come straight to me, Brian Ray, and I'll answer your questions and put you in touch with the right person coming out of this. Okay, so elements of cost. The first thing I want to go through is just how I think about the cost of developing a solution. Because as you'll see when we get to the end and we start digging into actual costs, that the cost of R&D is a big part of what it costs to deploy one of these solutions. So you certainly can't think, oh, this module costs $2 less than that module, therefore I need to use that technology, and think that that's the end of the story. There's a lot of really complex thinking and work that has to go on to get a solution like this built and tested and productized and out into the market. So I'm just going to quickly roll through, and this is really just to help you understand how I think about all of the different complex facets of building a connected product. So one of the first steps, after you figure out what it is that you want to build is hardware design and prototyping, which always begins with the electrical schematic. So which chip and components are connected to what on your circuit board, and that actually has a big driver into cost, because if you pick really expensive high dollar parts or parts that are very difficult to put on PCBs that maybe have a BGA ball grid array that have to be placed with very fine pitch, that can drive up the cost of your product significantly right at the get-go. The PCB layout's also important. The number of layers in your printed circuit board and the complexity there, again, those affect the cost. We always talk with a lot of customers about using a modular approach to electronics versus a chip down design. So in a modular, you've taken a little subsystem like a radio system or a power system that another vendor has done all of the R&D to put the parts down on it, all the testing and productization of that module, and then you put that module as a component down on your board. Generally, those modules cost anywhere from 2 to 5x what the chips inside of them cost, because you have to pay for those vendors to supply that solution. Going chip down always is going to result in a lower BOM cost, but your cost of development, certification, testing is always going to be higher because you have to pay for that development. Multiple spins. This is where the hardware designer and the team, especially when you're dealing with radios and complex enclosures and power requirements, they often have to spin the physical PCB multiple times as the prototype progresses through its life cycle. I don't think any IoT product in history has ever been launched on a single spin unless it's just a derivative of an existing design. We often see 2, 3, 4, 5 spins of prototypes before customers and products are a great fit for exactly how they want to go to market. And every time you do that, it adds cost because spinning prototype hardware is always expensive. Form factor considerations. I always like to say that industrial design and mechanical engineering are the hardest thing for electrical guys like me to figure out, because that really constrains the size and the layout of the PCB. So knowing what you want to do from a form factor and enclosure perspective before you start the electronics design is always going to result in a better better cost profile. Antenna selection. These are wireless devices that some need to connect over very long range, and you don't want to give up a lot of performance right from the get-go by picking a poor antenna. Little chip scale antennas, they may look great when you're browsing through DigiKey, but sometimes their performance is really going to eat your lunch. I already talked about component selection. In the DFM, design for manufacturing, design for test. One great way to save a lot of money is to make your PCB easy and cheap to assemble and easy and cheap to test. And a lot of hardware engineers don't think about those things from the get-go, but understanding how your design is going to be tested from an in-circuit test or a functional test, what kind of jigs are going to be used, having those requirements set in the beginning is always going to save a lot of time and money. In terms of what it costs to do hardware design and prototyping, it's wildly varies depending on how complex your system is. If this is just a simple 2-layer circuit board with some modular components going in an off-the-shelf plastic enclosure, probably $10,000 or less. But a complex new system with new sensors, just the hardware alone is probably going to run you $20,000, $30,000 in engineering. And then spins. That 200 to 300 each is actually each unit. It doesn't matter what your device is targeted to cost when you're in production, whether it's $10 or $100. When you spin prototype hardware, it's very expensive because new PCBs need to be built. Oftentimes components need to be hand assembled by contract manufacturers. So you got to budget, generally a good amount of money depending on how many prototypes you're looking to build. Just see a question here. Any thoughts on the importance of wireless costs versus hardware costs, which is more important? I think we'll get into that. I mean, I think cost is cost at some point, and where you spend your money kind of varies. So we'll get into that as we move along. The next component of development costs is industrial design and mechanical engineering. This is something that a lot of companies, especially that come from the software and the hardware side, overlook the importance and the cost of. Very good industrial design and mechanical engineering is expensive and time consuming and is very important. There's a reason that Apple spends so much time and money on industrial design, because their products look and feel great. Whereas slapping a circuit board in the back of a big NEMA enclosure might be very practical, but if the look and feel of your product's important, you're going to come up short. The IP rating or the protection rating, how water resistant, submersible, spray proof, temperature, shock, vibe, all of these things need to be considered. Some of these systems, especially the higher power radios like cellular, even LoRa, they can generate a lot of heat, and that heat needs to be dissipated or at least thought about in the design of the enclosure. Connectors, we all know that, especially things that need to be recharged, that have external antennas, how those connectors are mounted, protected, how the mechanical loads of those connectors are handled, all very important and need to be considered as you're building your product. Battery selection is probably #1 headache around Link Labs. There's all sorts of considerations to go into what type of battery a system uses. Most of the work that we do are battery powered devices, and it's not just as simple as grabbing 2 AA alkaline batteries, because for one, a lot of these systems require 3.1 volts or more, and if you can't supply that, you pay a big penalty in terms of power consumption. So that kind of brings you into the lithium realm, where you've got lithium polymer rechargeable batteries, primary batteries, but they're limited on the amount of pulse current they can supply, and then you need capacitors. So it's pretty complex, and you can pay anywhere from pennies to many dollars for batteries, depending on the chemistry, the form factor, availability, safety ratings. Really complex portion. And then antennas, I mentioned again. How the antenna is mounted and handled inside of the mechanical enclosure, again, is really important. We've seen customers spend well over 6 figures on going to the high end on industrial design. These are consumer grade products that have custom plastics that are manufactured with multiple molds. Whereas using an off-the-shelf enclosure, if that works, that can be a great way you can save a lot of money. But if you're doing plastic, just keep in mind that even after the engineering is done, a mold still has to be built, which can run you $5,000 to $20,000. And we've seen customers build molds in China, but then you have the issue of you have to ship the plastic after it's fabricated back across to wherever the electronics are being integrated. So it can get complex pretty quick. Firmware development. This is a big part of daily life at Link Labs. There's a lot of things that go into this as well. Powered IoT devices often use a Linux operating system because writing the software is so much easier when you're using a Linux kernel. Just a lot of the under the hood stuff is being handled for you after the kernel is built. We do mostly battery powered systems, which really can't use Linux. So we're using real-time operating systems or bare metal processors. There's all sorts of different things when you're doing even an RTOS or bare metal development, like building the bootloader, which is the thing that allows the system to load firmware either after it's been updated or when it's being programmed in the factory. Flash variables, these are the things that basically think of it like the hard drive for a system. So if the power gets cycled or the thing gets unplugged or runs out of batteries, when it wakes up, it knows what day it is and how to behave. Firmware updates, the ability to update devices over the air, so to speak, or even over the wire with firmware is very complex because you're handling, these flash memory down at the register level and just keeping track of all of those and encrypted binaries, very complex. Test modes that the devices will go into when they're being fabricated, or compliance test modes, like when you're doing FCC testing to generate tones and sweeps and other things to make testing easier, all go into firmware development. One thing that we always encourage customers to do is add debugging and logging into their runtime software, so they have more information about what's happening in devices, both for kind of a legal requirement if this is a safety critical device, but also just to help as the product is young and maybe having issues in pilots, you can actually have something to go and chase down to debug. Software and application development. This is software development that many people are more familiar with. This is web-based software in servers and web browsers where the actual IoT information and device and sensor data is being processed and handled. There's a lot of companies out there and a lot of products that make this easier. There's different platforms you can use. You can do it yourself by building web services using AWS or Bluemix or other cloud hosting platforms. There's also a lot of infrastructure as a service. AWS has a lot of this. There's PubNub and other things that make moving data in and out of databases and in and out of devices much easier. AWS has their new IoT framework and Greengrass and other things. Frameworks, I'm talking here more about front-end, browser frameworks like React, Angular, et cetera, that make building web applications easier. Obviously, there's the mobile side of that as well. It's always also important to think about scalability and robustness. Web servers crash, you've got memory problems, who knows what, and having systems that don't just completely go dark at 4 a.m. Is really important. And then, this is definitely the part of the system that will continue to change over time, because how humans interact with your product is going to evolve as you sell and grow into the market. So being able to manage the requirements and manage a software team that can be agile and continue to improve over time is important. It's hard to put a number on what these costs. Building a proof of concept beta software using existing frameworks is generally around $10,000 to offshore it. And if you have an in-house team with a big budget, certainly 6 figures. Design for manufacturing, I touched on that a little bit earlier, but it is definitely an important element of the cost. Supply chain, sourcing, assembly, etc. Testing, this is both usability testing, unit testing to make sure that your product is doing what you think it's doing and can survive different edge cases, but also FCC, EMI testing as well. And then certification, we're talking about wireless systems. So those are governed in the US by the FCC, in Canada by IC, in Europe by ETSI, and every country has a regulatory body that handles the wireless spectrum and interference issues in those countries. And then you also have UL certification, which is an optional certification for safety devices or devices that plug in. It's mostly for keeping things safe from fire, damage, etc. And then carrier certification. Some of the technologies we're going to talk about here are cellular, and so being certified to be on a mobile network is an important part of certification. And simple devices that just need an EMI check from FCC, you're looking at $3,000 or less, but full global carrier PTCRB certifications easily going to run you over 6 figures in a lot of cases. Okay, I'm not going to keep beating a dead horse on all the elements of cost, but just to talk a little bit more about manufacturing. This is as devices are scaling, there's a lot of costs that can creep in. Contract manufacturing, these are companies that their business is to make money building products for you. So your costs will vary widely, and some of these companies are very good at making sure that they're going to extract the maximum amount of money from you as their customer throughout the life cycle. So maintaining the flexibility to move your product and design around is important. Managing lead times and end of life on components. Chips go out of fashion, different parts can be end of life, and managing the amount of inventory that you have and being able to continue to buy your product as you build it is critical. Unit testing, most of these products need to be tested one by one as they come off the assembly line to ensure that they function. Things get put in boxes, they get shipped around the warehouse, and distribution of product all is adding cost to your product as it's rolling out. And then once you have a product in a box ready to sell, demoing and piloting is expensive, because oftentimes you're essentially giving away hardware for free with the hope of making a sale. And if you don't manage your sales team and your marketing team's ability to get product out of operations to go out and pilot and demo, the cost can add up quickly. Installations, if you're doing networking equipment or putting in equipment in enterprises or industrial settings, the cost of labor, materials, cabling, all of those things go into the ability to be cost effective. And then support, troubleshooting, returns and repair, and then finally connectivity costs is one of the things that we're going to really dive into here. These are just all of the things that go into what an IoT system costs to actually build and deploy. So IoT, in my mind, generally means wireless. So generally, you're connecting your device to some sort of data system. If I break down wireless connectivity into 3 big buckets, I see customer supplied, where you're selling a device that's going to connect to a wireless network that the customer is providing to you. And generally, that's Wi-Fi or Bluetooth. A vendor-managed low-power wide area network. These are things like LoRaWAN, Symphony Link, which is our product, but additionally, things like mesh technologies and other things where you're installing the infrastructure on site, or at least providing the pieces of it to the customer to install on site for the system to work. And then finally, you have the network operator model. This is pretty easy to understand. This is how cellular companies or MNOs, mobile network operators, operate. LTE, NB-IOT, Sigfox, Ingenu, LoRaWAN operators. We'll dig into what all those things mean here in a minute. But these are the 3 different connectivity options that I see. How are we doing, Glenn? You chatting away over there?
I am answering a lot of questions. Just a reminder that forum.linklabs.com is where people can ask questions outside of the scope of the.
Yeah, any questions you have, just shoot on over to forum.link-labs.com. We'd be happy to dive in with you there. Okay, so customer supply connectivity. A lot of people are familiar with this. Here you have generally a phone, handset, Android, iOS, which is connecting to some sort of sensor, generally using Bluetooth Low Energy or Bluetooth 4.0. Then an SDK or software development kit is running on some app that gets the data from BLE or pushes it back down, and then uses the phone's network connection, which is your Wi-Fi or LTE, to push that data up to a cloud application. I think this is a fine architecture for consumer-only products, but I've experienced time after time, enterprise or industrial customers saying, we just can't rely on the phone of our employees to be the data path, because a lot of it's bring your own device, and they're just not comfortable requiring their employees ferry the data from their operational sensors. And then there's just all sorts of risks that introduces. So generally, Bluetooth to phone, I would say, is limited to consumer products. And then we do a lot of work at Link Labs replacing Wi-Fi, where early on customers thought that they could build a Wi-Fi connected sensor for industrial enterprise setting. But as it turns out, just because there is Wi-Fi where you want to sell your product as a third party, oftentimes you still can't connect to it. And that comes down to really two things. One is just provisioning. There's like 5 different deployed Wi-Fi standards, different types of security models. Passwords change, you've got challenge screens. This little IoT device, it's actually really hard to tell it, get it a password or a certificate and manage it to be able to connect day after day, year after year, as the Wi-Fi network's changing. And then these days, the prevalence of Wi-Fi connected devices being a vector for LAN cyber attacks mean that a lot of IT teams just are no longer comfortable with third parties connecting little Wi-Fi based sensors to their corporate networks. And obviously there's workarounds for that. There's DMZs and other technologies to make that easier, but that is a very common challenge that we see to using Wi-Fi or for your connectivity. And then as I get into these, different technologies that are coming up, I just want to pause here to talk about, how much data these things are using, because this becomes one of the most important drivers of the cost. So a typical sensor message, whether it's a GPS position, a temperature, proximity read, etc., generally those fall into the 10 to 20 byte range. We're not talking megabytes of data here, even kilobytes. Oftentimes these readings are relatively limited. But when you add the overhead associated with HTTP, TCP, which is a typical protocol stack of sending messages from devices up to clouds, you're often adding 900 bytes or more just for that one 10-byte message. So you could easily be looking at over a kilobyte just to send a 10-byte message using an IP connected technology. Now, one of the things we're very focused on at Link Labs is how do you get that data bill on LTE-M or another technology closer to the actual payload that you're using. And there's all sorts of ways to do that using different protocols, compression techniques, binary protocols, UDP sessions, etc. But the rule of thumb I always like to use as an entering argument is if you're using an IP-based network technology, assume you're using a kilobyte for every message that you're sending when you're calculating how much data you're going to need to buy from the mobile operator. Okay, so I want to jump into LTE Cat M1. This is a technology that's a huge focus for Link Labs. In the US especially, it is already deployed on multiple mobile networks, Verizon and AT&T. But what is it? We're all familiar with 4G LTE, which is how our iPhones and Android phones connect to the mobile networks to move a lot of data very quickly. But M1 reduces the complexity of LTE, but still works within the same LTE framework so that it can be overlaid inside of existing LTE networks without much impact. It also has a much simpler front end. So you're taking what used to be a 20 megahertz or more LTE front end for your iPhone and reducing it down to about 1.5 megahertz. And it only has a single antenna. It's not a multi-antenna array. So the chipsets that support it are much, much less complex and therefore much, much cheaper. that comes at the cost of much lower data rate. It's about 1 megabit per second or less half duplex. So your effective throughput is probably 100 kilobits per second or less bidirectionally using Cat-M1. But that's still enough to support compressed voice, sensor data, etc. And then the two innovations of Cat-M1 that make it as power efficient as other technologies are power saving mode and EDRX, or extended discontinuous reception. Power saving mode is where a device can tell the network, hey, I'm going to go to sleep, but when I wake up, don't make me re-register and go through this complex, power expensive process to get back on the network. I'm just going to wake up, send a single message, be pageable, and ready to send and receive data. And EDRX says, hey, base station, I'm going to wake up every 40 seconds, 2 minutes. There's all sorts of intervals available, and listen to see if you have traffic for me coming down. And I don't want to have to transmit every time. So this allows devices that want to have low power budgets, but still need to be reachable to do things like, turn valves, turn off electric loads, etc. So these two things combine to make LTE Cat-M1 a really power efficient, really powerful technology. Because of all the technologies we're talking about, it is by far the fastest, meaning the most data can be moved. 100 kilobits per second may not sound like a lot, but compared to some of these other technologies I'm going to talk about, it's like a Ferrari. Just a quick plug for Link Labs LTE products. We manufacture a module which has a simple UART API to send and receive messages. You don't have to handle any of the complex AT commands or cellular drivers. And we have built-in power and data consumption control so that you can send and receive simple messages, send 10 bytes, get charged for 10 plus X bytes, and we manage all of that complexity so you can focus on building the application and your system without having to count bytes going back and forth to the mobile operator. In terms of coverage, LTE-M1, especially in the US, is by far the most common IoT network available. Here's a Verizon network map. You can see their LTE-M1 coverage is pretty much everywhere where people are in this country. When I show you the coverage maps of other technologies, you'll see a pretty stark difference. In terms of pricing, I just copied and pasted these off. This is the Verizon, this is the AT&T pricing off their website. Verizon has a more traditional, per byte per month model. They have 200 kilobyte plans starting at $2 a month, up to a megabyte for $5 a month. AT&T has more annualized pricing, where you can pay by the year, by the megabyte. So here's a plan. If a device has 3 megabytes to use inside of 3 years, which is a $45 one-time charge. Now the gotcha is when you go to 3.1 megabytes, that doubles and you get 3 more megabytes. So it could be expensive if you aren't really in touch with how much data you're using. But if you go on the AT&T site, these plans go all the way up to 10 years at a time. So a pretty good way to really control costs, but you have to be careful on overages for sure. NB-IOT is a technology that's getting a lot of attention as well. It's very different than LTE-M1. It's a new technology in the sense that it doesn't fit inside of the standard 4G LTE framework, and it can be deployed in a couple of different ways. It can be deployed in 200 kilohertz of standalone spectrum inside of an old GSM block, on the guard band of UMTS or LTE spectrum, and it can actually be installed or used inside of an RB or resource block in LTE. It's another half duplex technology. It's much slower, and it's not IP based. It's message based, more like a LoRaWAN or a Sigfox, but certainly has a higher data rate there. And the chipsets, they can be slightly less complex. There are some OFDM or rather complex physical layer technologies used. So I don't see them being dramatically cheaper than LTE-M1 chips, but slightly cheaper. And I think a lot of chip manufacturers are going to support both modes in the same chip, which means the price is going to be pretty much equivalent. And I don't think we'll see a lot of this technology in the US for a long time, but there are trials underway in the EU and China. Vodafone is a big proponent of NB-IOT technology because, as you'll see later on, it stacks up really well against other LPWAN technologies like Sigfox and LoRa that are doing well in those markets. Sigfox, this is this industry is a pretty young one, but this is really the granddaddy of technologies that got a lot of interest started here. Sigfox is a very, very simple system where devices transmit simple, small 10 or 12 byte message 3 times and just hope that the base station receives it. This is a spectrograph showing a number of Sigfox messages being transmitted simultaneously. And another nice thing about it is it uses stock, very inexpensive UHF RF chips that are available for $2 or so. It's completely asynchronous, meaning that the devices just wake up and send. There's very limited ability to send messages down to devices with any type of consistency. So it's mostly for meter reading and other low-cost, low-end, low-performance type applications. But here in the US, I think the biggest limitation is the coverage. I took this screenshot earlier today on the Sigfox website, so you can see that the number of cities and areas that are covered, which are shown in this aqua color, are relatively limited. So if you're trying to sell a tracking device that's supposed to work everywhere in the country, certainly Sigfox isn't the one for you. But if Abilene, Texas taxi tracking is where is your application, then deploying where Sigfox has coverage could be a great option. LoRaWAN is another technology that is a little different than Sigfox because it can be used both as a public network technology and a do-it-yourself private technology, more like Wi-Fi. It uses this dumb gateway smart cloud where one or more gateways hear messages and then move the data up to the cloud. It has some limitations just because it's completely asynchronous, or it's a low-hop protocol. So you can have a lot of collisions and message loss, but it's a very popular technology. The range performance is very good. I put a lot of stuff out about LoRa and LoRaWAN, so feel free to crawl over our website. You'll find more there. LoRaWAN in the US, this is a coverage map of a company called Senate, which is deploying LoRaWAN networks, mostly for tank monitoring and agricultural applications. So you can see they're heavy in the California area and St. Louis and other places. And actually, I think probably more coverage than Sigfox at this point. But again, nowhere near nationwide, nowhere near a technology that you could, box something up and sell on Amazon and expect to be able to connect. That's not the case. Interestingly, Comcast, through this project they call Machine Q, is piloting LoRaWAN in a number of cities as a way that they, as a cable operator, can provide an IoT network technology. So certainly keep your eye on that. A little bit here, LoRaWAN, like I said, we built our Symphony Link technology to address many of the issues that our customers see with LoRaWAN. I have a lot more out there if you're interested in this particular feature. Ingenu is another company that is in the IoT network space. They use a 2.4 gigahertz CDMA technology. It's a coded technology. And they've deployed it in, again, a number of cities you can see throughout the US. It has a lot of great features, actually. It's very similar in many ways to Symphony Link. Some downsides are, again, it's very limited network footprint, a limited supply of modules, and it's a relatively legacy technology, but it's a great fit for a lot of fairly complex IoT solutions. I think I've never worked with Ingenu technology. I see a lot of risk just from a corporate and company perspective. I know that they fired their CEO last week, and I think it's an uphill battle for a company like that to deploy a network to compete against Verizon or AT&T. But I thought they were worth mentioning. Here's a slide I found on their website about how they look at multiple spreading factors and different durations. So a lot of capacity in their cells and probably a lot of great link budget. But again, I think that the business side and their deployment challenges are pretty great. Our technology, Symphony Link, just to quickly address it, is meant to be a campus or a private network type technology that's similar to LoRaWAN, but adds a lot of features. It's a very different protocol stack. It has 100% bidirectional acknowledgements, repeaters, very robust firmware over the air, multicasting, etc. But plenty more about that if you're interested on our website, and get in touch. So, How much does it cost to use any of these technologies? Well, I took a stab, again, back to my caveat early on. These are not meant to be the prescriptive pricing. This is what I could find. This is what I think. You're welcome to disagree. LTE-M is probably the most expensive from a module standpoint. It's definitely the most complex chip in this chart, but still $10 to $15 for a module is pretty good. Connectivity-wise, I put $3 to $5 a month for 1 megabyte. I think that the LTE-M1 pricing will mature over time, but I think that's a good place to start. NB-IOT, I put the module slightly cheaper, and the pricing that I have seen, which is again very notional, since NB-IOT is not really a deployed technology yet, is very low, but it's also focused on very low data consumption. So here I've got less than $1 a month, but that's for 100 kilobytes or less, which for a water meter might be enough, but for an asset tracker or something more complex, you're probably going to run right over that 100 kilobyte limit pretty quickly. Sigfox, definitely the cheapest RF technology. Connectivity-wise, they say less than $1 a month. I think that's pretty fair, but again, you have the challenge of network availability. Ingenu, I'm basing this off of the U-Block's pricing I saw for their module, and then I couldn't get any answers on what connectivity costs for Ingenu, but I'm guessing it's in the $1 to $3 a month per device range. I've got LoRaWAN on here twice because there is really two different models for LoRaWAN. One is the public infrastructure where you're connecting to a Comcast or a Senet, or if you're in Europe, there's a lot of LoRaWAN network operators, Orange and others. Modules for LoRaWAN, for Microchip or Murata might be in the $8 to $9 range. And connectivity, again, it varies. Orange has some pretty interesting pricing on their website around the number of messages you can send, the amount of downlink messages you can send. So it varies. $1 to $2 a month, I think, is pretty fair. And then at the bottom, I've got two private network options, which is you buy the infrastructure, you deploy it, you connect your nodes to it. This is LoRaWAN, private, and Symphony Link, our product. Our modules are a little bit more costly. They're a lot more complex to handle the protocol. But from a connectivity and infrastructure side, you'll see which particular use cases using a technology like this you can come out ahead on cost. How are we doing on questions?
Here's one.
Glenn is going to post that for me. So some use cases I want to dive into for really jumping into price or cost. Asset tracking with GPS, asset monitoring using Bluetooth, this should say smart metering, smart meter reading, or meter reading, and then smart building, consumer, and a consumer monitoring device as well. So asset tracking with GPS. This is an eye chart, but just to break it down. So I think that if you're building 10,000 of some GPS tracking device in a case, ready to go on a bicycle or a truck, you're looking at about $30 of BOM assembly and testing and packaging costs without the radio. You can see the numbers I picked for these different things. This is just based on some experience I have. You can pay more, you can pay less. Again, this is not meant to be prescriptive. I took the module costs from an earlier slide and jammed them on top of this baseline BOM to come up with these costs of the BOM using different technologies. So you can see LTE-M is the highest, Sigfox is the lowest, and everyone else in between. Now, assuming that you send one message at one position every 15 minutes, 30 days a month, I estimated that your LTE-M cost would be over 3 years, so this is not per month, at $144. NB-IOT is higher because I think the per bit cost of NB-IOT when you get up to that level, which is around a megabyte, is higher than LTE-M. I put Sigfox and LoRaWAN in here at their $1 a month price, but I think for both network technologies, sending data once every 15 minutes is more than those networks generally support. Development-wise, I'd put $200,000 on here, which I think is an okay budget to start from scratch to build a new product. So you can see the loaded cost per month per unit if you have a 3-year payback period, is broken down here. $5.80 for LTE-M, $7.28 for NB-IOT, and Sigfox and LoRaWAN at just over $2.50. But again, I don't think that those technologies would support the amount of data that needs to be sent here. And again, you have the network availability issues. Glenn's put up here, why don't you highlight what you want me to address, Glenn? What do I expect the mature price point for LTE-M to be? That's a tough call, because keep in mind, Verizon and AT&T want to make money doing this. So I think that many use cases that are sub 1 megabyte per month are going to be in the $1 to $2 per month range. I think NB-IOT is going to be cheaper for small amounts of data, and we've already seen that. But again, and we'll show this in the next slide or coming up, that's really targeted more at that AMR, automatic meter reading, very infrequent use case. A couple more caveats just to consider. I think Sigfox and LoRaWAN are great technologies for simple use cases, but your ability to do things like update device firmware, send control messages down to turn like GPS on and off based on different rule sets, are very limited. So it may be tempting to look at Sigfox and LoRaWAN costs and be like, oh, why would I ever use LTE-M for a GPS tracker? Well, it may be that that's the most expensive $2.50 a month that you ever face, because you can't update the device, you can't turn it on and off. So just really understand the implications of the technology you choose when you're considering the costs of it. I just wanted to throw this up here. This is an architecture of how we use a combination of LPWAN technologies in our AirFinder product to really drive down costs. So here we have Bluetooth low energy beacons providing reference points to tracked assets, and then they're sending that data using BLE to reader devices that then send that reading information up using Symphony Link to gateways, which are connected to cellular, or direct via Cat M1. So just kind of keep this architecture in mind as I go through the next example. If you're looking to monitor a large number of devices on fixed sites, consider using a Bluetooth in combination with an LPWAN technology. And here's why. If I have 500 sites, each with 100 sensors, which give me 50,000 sensors, just 500 times 100, and those sensors cost me $10 each, which I think for a Bluetooth low energy sensor is achievable. They're globally available. There's all sorts of sensors out there. If those sensors are coming back to gateways, call it $500 in cost, and you're paying on average $15 a month for gateway for cellular connectivity and platform management, and you spent $200,000 in developing the system, your cost per sensor is 68 cents per month, amortized over that time. So that's way less than $2.50 or whatever it was for one of these other systems. And it's a combination of using the lowest cost hardware out there, which is Bluetooth, and doing this one-to-many architecture where your expensive cellular connectivity is at a gateway where you're backhauling 100 sensors at a time through it. So this is an architecture that we always recommend to customers if they have a fixed site with a lot of sensors. It's when you have only a few sensors that need to go anywhere that we push people toward LTE-M, because the headache of not having to manage the network infrastructure goes away. Meter reading. This is really the other end of the spectrum from like a GPS monitor. Here I'm assuming 1 message per day. I've got some notional hardware cost. I say $24 if you want to be aggressive with no radio and no sensor. Obviously, you're not going to get a water register for under $24. Adding in the cost of the radios drives you into the $30 to $40 range. But here, if you look, I modeled the cost of NB-IOT at $27 because they've said, sending 100 kilobytes or less per month, which you could certainly do in this use case, drives you less than $1 a month. LTE-M though, here we're still kind of at that $1 to $2 a month range. This fixed 200K development budget stays the same. And here you can see that NB-IOT now is competing right in the same price points as NB-IOT and Sigfox and LoRaWAN. And that's, I think, what the technology was designed for. My guess is that 5 to 10 years from now, you're going to see, millions of meters using NB-IOT. Your water meter, electric meter, things that need to be connected everywhere but don't have much to say. Where more heavy IoT type solutions, GPS, sensors, smart, air conditioners, et cetera, LTE-M is a better fit. The same caveats I had before around firmware, firmware downlink, controllability, network availability could still apply here. Smart thermostats. So this is a smart building type use case where honestly private deployed network technologies are probably the most prevalent. That's really why Zigbee exists. You can use technologies like LoRaWAN and Symphony Link as well. Here I put $26 with no radio. Add the radio again, it gets you in that same $30 to $40 price point. Here I'm assuming one message every 15 minutes, which is pretty common for a smart thermostat. You can see your NB-IOT price jumps up above LTE-M, and I modeled again Sigfox and LoRaWAN at kind of their published pricing, but said you're probably not going to be able to support a device like this if it's sending data that frequently on those networks. And so you can see your costs are similar to what you saw with GPS, but NB-IOT with even greater usage is probably even more expensive, and the same caveats apply. So that's it. I just wanted to lay out really these different parts. You got the baseline hardware development, the module costs, just to spend a little bit of time talking about modules versus chip down. I always recommend that customers go with a module during the prototype phase. The reason that you would go chip down is because you're really trying to eke out every last penny of your BOM design. But as I showed here, the cost of the module is already less than 5% of the loaded cost of development of your system. So your max savings maybe is 2 to 3% of your 3-year budget, which might not be worth that larger R&D outlay in the beginning, and certainly the slowing it down. And it's also going to drive up your certification costs to the point where your break-even point of going chip down is probably way out beyond 10,000 pieces. Another conclusion here is that data usage is by far the largest variable cost for a lot of these technologies. NB-IOT especially, LTE-M is structured in such a way that it's probably 10 to 100 times more expensive per byte than your smartphone's data plan. So keep that in mind. Another conclusion, some networks are not available everywhere. Sigfox and LoRaWAN are very interesting, innovative technologies, but they don't exist everywhere. So you can't use them for a lot of applications. And don't believe all the hype and press releases. Try out the technology where you want your device to work, in buildings, in cities, etc. And then finally, this one-to-many architecture using technologies like Bluetooth and other things in combination where you have fewer cellular bills to pay can really save money. And that's the primary reason that we use Symphony Link in some cases here at Link Labs. I'm going to pause there. Glenn, are there any questions that have come up? Isn't the battery cost of cellular solutions way higher than LPWAN? I would say, so the power budget of LTE-M versus a technology like Sigfox or LoRaWAN is higher. It's about 30% higher bit per bit if you use PSM and EDRX well. But the difference is when the LTE-M module is transmitting and joining the network, it needs to draw more current than you need with an LPWAN technology. So that forces you into bigger or more expensive batteries. But again, I would come back to is the network even available? Like I said early on, if Sigfox existed everywhere in the US, it would be an awesome fit for a lot of use cases we see. But we just can't recommend it to most customers because they're not only in St. Louis, they're also in Denver where there's no Sigfox coverage. And just given the nature of those companies, Sigfox, Ingenu, Senet, it's hard to put all your chips behind those companies continuing to exist and grow over time when Verizon already has the network, it already works great. Just because you need to use a little bit bigger battery, might not be the downside that a lot of people think it is. Any other questions, Glenn?
Yeah, there's some more questions about battery. So it's a good point. I mean, people need to take that into consideration in their application. There's no right or wrong answer.
Yeah, exactly. Especially in Europe, Sigfox and LoRa applications, they transmit at 100 milliwatts or less, meaning that the amount of power that the battery needs to source is relatively limited. LTE and NB-IOT technologies can transmit at 20 or 23 dBm or 100 milliwatts or more. it requires more oomph from the battery. You know, you can't use even like a primary lithium battery to supply 300 milliamps of current at 3 volts. It's just not going to happen. So yeah, again, back to the overall system design, what network we are going to use definitely informs what battery, you know, choice you want to make. Any other questions? Great. Well, hey, I enjoyed this. Again, reach out to me at webinar@link-labs.com if you have a question for me, or jump over to our forum site, forum.link-labs.com. That's probably the best place to have a discussion. And thanks again for joining. Take care.